This meeting summarized.
Can we start?
Yes, ma'am. We can start.
Sharing the slides.
Hello. Yeah, welcome back, participants. We will now begin the hands-on session with Professor Namita Mittal ma'am on the topics she covered in the first half. Ma'am, you can continue.
Yes,
Hello.
we are continuing. How can we share the GPT notebooks?
Yeah, you can send to the host, ma'am. Send to the host, ma'am. He can share.
Host means Dr. Bhaskar.
Yes, ma'am.
हाँ, आपको भेज देगा, सुष्मिता को भेज दे। कर सकते हैं शेयर। Please give us a minute. We are sharing the notebooks so that we can do it parallel, right? So it has been shared. It has been shared. Please see the chat. and download it at your desktop. There will be a, you see a link, NLP notebooks. Thank you, Dr. Gyan Prakash Chandra ji. Others also please do it quickly. So we are giving the access to you. Please. You are allowed to copy the code and download it here. आपकी computer पे. You need to download in your computer. You cannot change at Google Drive. Otherwise, it may have some issues. Please download it at your end and run it.
Ma'am, I think it's showing access denied, ma'am.
Kindly check it once again. Refresh it. It has been given. You have to copy, download. You have to copy and paste it in your Jupyter notebook. Please refresh it because once it was denied, so it will not continue. You have to refresh it. So access has been given to you. For the viewer purpose, just copy, paste it in your notebook. Again, the link has been sent. Please see. Shared. It is shared. So now happening. Yes. So one participant, Shridev Deshpande ji, has confirmed that it's happening now. Good, thank you. Thank you, Joseph ji. Thank you. Okay, go ahead, please. Yes. Give me a second. Am I audible?
Hello.
Hello.
I welcome you all to the hands-on session of natural language processing and one of the most important topics in NLP, that is text representation. So in this hands-on session, the prerequisites will be Python, statistics, machine learning algorithms like supervised learning and unsupervised learning, and some deep learning basics that like activation functions, optimizers, and loss functions. So this hands-on session, we will be covering in 3 sections. The section 1, in this, I will be giving you an overview about the libraries of NLP that is used in mostly all of the NLP applications. Second one is the roadmap to NLP. And the third is the text pre-processing, in which we will be covering tokenization, stop word removal, stemming, and lemmatization. In section 2, we will be covering the text representation and embedding techniques. In this, we will cover one hot encoding, bag of words, TF-IDF, and word-to-vec with the two architectures, that is continuous bag of word and skipgram. In the section 3, we will see an end-to-end pipeline of any NLP application that you can use whenever you are creating an NLP application. So in section 1, the overview of the NLP libraries, roadmap, and the text pre-processing techniques will be covered. So the libraries we use for NLP are like for data handling and numerical computation. These are the support libraries. So we use NumPy, Pandas. So it is used for data pre-processing, manipulation, and numerical computation required before the NLP modeling. Some basic NLP pre-processing like tokenization, part of speech, NER. For this, the library we use are NLTK, PACY, and Stanford Core NLP. So these are the core NLP tasks like tokenization, pause tagging, parsing, and NER. The third is for creating the word embeddings. The library we use is GenSim. So it is used for generating the word embeddings and performing topic modeling or text classification. And the fourth is the traditional machine learning library for NLP, that is scikit-learn and fasttext. So it is used for classical machine learning based text classification using TF-IDF, bag of words, and shallow models. It's a quick overview. I believe that everyone is already aware of these libraries. So NumPy arrays, it is a numerical processing library that can efficiently handle large data sets stored as arrays. It is used for numerical computing with n-dimensional arrays. So it also supports factorized operations, linear algebra functions, matrix operations like multiplication and inversion. and statistical computation, including mean, median, and standard deviation. And moreover, it can easily integrate other libraries like Pandas, SciPy, and Scikit-learn. The second most popularly used library is Pandas. It stands for Panel Data Library. So it is one of the most popular one and it is built on NumPy. So using this library, we can perform series, data frames, missing data, group by operations, and standard input-output operations. So it has a built-in capability of data visualization using series and data frame, which are built upon matplotlib. This library is the most commonly used library, that is NLTK, Natural Language Toolkit. So it is a versatile library designed to simplify NLP with functionalities including text processing libraries and pre-trained models. With the help of this library, we can do tokenize text into words. We can segment the words into syllabus, determine the part of speech, and then calculate the word frequencies. So these three libraries we are going to use for the demo purpose in the hands-on tutorial right now. So if we see a roadmap to NLP, first we are going to perform text pre-processing. In this step, we perform the text cleaning using the techniques like tokenization, stop word removal, lemmatization, and stemming. The second step is text representation, in which the text is converted to the vectors and the relationship between the two words are framed. So this is done using the bag of words, TF, IDF, and ngram. The third we perform is the word embedding. In this, we convert the vectors to embeddings using the techniques word2vec and glow. And fourth is the machine learning and deep learning algorithms. We can use RNN, LSTM, attention models, and transformers to complete the entire application. So this is the basic roadmap that we will be following whenever we are creating an NLP application. So now the question arises that why the processing is important. So it improves the accuracy. One can get the best results in terms of efficiency and accuracy with the clean and well prepared data. It reduces noise. So it removes all the irrelevant and redundant information. It standardizes the data so that text is converted into an uniform format and can be used globally. And fourth is it enhances performance. So it reduces the complexity so the models can be trained faster. So now in the, tokenization, the in text processing, the text or the sentences are converted into words. So after tokenization, we do stop word removal. Then we do perform stemming and lemmatization. If we see in tokenization, the example I have taken here is a spam classification. Am I audible to everyone?
Yes, madam, you are audible.
Okay, yes, thank you so much. Uh, so in tokenization, we are going to see an example of spam classification. So if we see here, there is F1 and F2. So these are the two independent features. F1 is the email body and F2 is the email subject. And the output is classified as spam or ham. So the step one is tokenization. So in this, we are converting sentences into words. So if we see the sentence as price for you, free holiday. So all these words will be converted into tokens. So now we have 5 words over here. So these are called tokens in NLP. So the tokenization will actually give words from all the sentences. In the second step, we are doing the stop word removal. So if you see here in this example, NLTK is a leading platform for building Python. So the words like is, of, the, to, these are all the stop words which are actually not adding any meaning to the context here. So, but we have to note here that the word not is important because it can change the meaning of the sentence. So we cannot put it in the stop words. So NLTK actually does not include the word not in the stop word list. So now the question arises that can we have our own list of stop words? So the answer is yes, we can define a list of words that can be considered as stop words. In the third step, we are performing stemming. So in this process, we are finding out the base or stem of the word. So the process of reducing the word to the base word is called stemming. For example, if we have here 4 words like change, changing, changes, and changed. After stemming, it will give the word chang. But if you can see, this actually does not hold any meaning and it is not present in dictionary also. So the disadvantage of this technique is that the base word may not have any meaning. So to overcome this, we are using lemmatization. So similarly here also we are going to find the base or the stem of the word which actually has a meaning. So it has a dictionary of its own and it performs comparisons. So we have already seen this word which is change and after stemming it is going as chang. But in lemmatization we are getting a word change here. So it is actually a word in the dictionary here. So although this technique is useful, but it has disadvantages like it is slow because of all the comparisons here. So now if we see the notebook one that I have just shared, so in this notebook, we will see a quick demo of all the text pre-processing techniques we have just discussed. We will be removing the special characters and non-alphanumeric characters, which add no value to the text. And in second, we will be converting it into the lowercase. Third step, we will be removing all the punctuation marks. And the fourth step, we will be doing tokenization. Fifth will be we will remove all the common words like all the stop words present over here. And in the sixth step, we will see lemmatization and stemming of the context. In section 1, we are going to import a library called RE. This library is used for pattern matching in the text and it is for regular expressions. In this step, we are going to define a function to remove the special characters. So we are defining the function as remove special characters and numbers and passing the text as the parameter here. The pattern here we is defined here is to match anything that is not a letter or a space. And after all the matching, the function sub is used to change it and to substitute the pattern found and replace it with a new text. And this function will be returning us the clean text over here. So if we take an input example, it is success isn't final, and there are many punctuations mark also that will be that we will moving eventually in the another step. So after calling this function and printing the clean text, you can see that all the punctuation marks and everything are removed in this step. So we are removing all the special characters and non-alphanumeric characters in this step. In section 2, we are lowercasing the entire input that we are giving to ensure the uniformity. So for example, we are taking the text as learning new concepts improves your knowledge. So you can see there some words are capital letter and some are in small. So we are going to use an inbuilt function that is lower. And after converting the input text, the clean text will look like all in the lowercase. In section 3, we are going to remove the punctuation marks. So this code removes all the punctuation marks from the sentence using the Python's built-in string library and the translate function. So we are importing the library string, passing the text here as an input. And after translating it, we are removing all the using the make trans functions and passing the parameters. First will be the characters to replace. The second parameter is the replacement characters. And the third is the string dot punctuation, that is the characters to delete. So we are removing all the punctuation marks over here. You can see in the display of this section that all the punctuation marks like semicolon, asterisk, everything is gone over here. In section 4, we are performing tokenization. For tokenization, we are importing the library called NLTK. And from NLTK, from tokenized package, we are importing word tokenized and send tokenized methods also. For example, we are taking a paragraph over here as an input. And you can see the paragraph like India has one of the fastest growing major economies and so on. We can download the additional packages for sentence splitting and pre-trained tokenization models as Punkt and PunkTab. So these are the packages that are provided in NLTK library only. In this step, we are performing tokenization on the sentence and then on the words. So in sentence, NLTK.sentence tokenize, we are passing the paragraphs, and this is converting the paragraph into the sentences. And in word tokenization, using word tokenize method, we are passing the paragraph, and this is converting the sentences into the words. So in the display, you can see that the entire sentence in the first line, India has one of the fastest growing and so on, has been converted into all the unique words present in the corpus. In section 5, we are removing all the stop words. So again, we are downloading the NLTK library, and from the nltk.corpus, we are importing a stop word method. So we are downloading the package stop words present in the NLTK to get all the stop words that are understood by NLTK library. In this step, we are taking the words in English. It will return a list of all the English stop words present in NLTK. So now the question is, why are we converting it into set? So because set allows us to hold all the unique elements. It is mutable, that is, we can change it, we can add or delete any stop word we don't want, and it is also for faster lookup. So that is why we are converting it into set. In this step, we are removing all the stop word. So using this function, it says that each word in the list will iterate through all the words and convert the word into lowercase and then keep the word if it is not a stop word. So using this function, we will be filtering out all the words and removing all the stop words. So if you see the display, the original words were India has, one, of. So now the words like of, the, in, these do not add any meaning to the context here. So that is why they are removed after this section. In this section, we are performing stemming. So again, we are going to import NLTK, and from NLTK stem, we are going to import the porter stemmer function. We are going to initialize the porter stemmer in the step, and then the stemmer, with the help of a stem function, we are going to reduce the word to its root form. So and as we have seen in the slides, the word changing, the stem word of this after stemming will be chang. So now to convert the entire word from the paragraph, we are passing the paragraph over here in this step. So the each word from the list will iterate over all the words, and then stemming will be applied to each word over here. So now if you see in the display, the original text is already given. India has one of the fastest growing and so on. And if you see the word like economies is converted into economy with I in the ending. And similarly, other words like mixed here is converted into mix. So these are the stemmed word of the original word over here. In this section, again, we are going to perform lemmatization, and for that we are importing an NLTK library, and the word net lemmatizer is the function we use for lemmatization. we are going to download a large lexical database for the English word that we will be using in lemmatization. So we will be using WordNet for it. Here we are initializing the lemmatizer and then changing the word with the help of a function to its base word called lemma. So now here the word changing is going to be like changing that has a meaning in a dictionary. So after applying lemmatization to all the words in the paragraph, you can see in the displayed section, here the word economies, the base word comes as economy over here, which is actually a word in a dictionary. Similarly with the other words also. So you can try these techniques with any paragraph of your own and then play around this section over here. So here we end section 1. You can do this assignment whenever you have like after the session. So you can download any text dataset available online like IMDb reviews, Twitter sentiment dataset, news headlines dataset, which are available online and publicly open for everyone. And you can perform the basic data exploration using NumPy, Pandas, NLTK. And if you need to know more about all the operations which particular library offers, you can follow this documentation over here. And then using NLTK, you can perform the pre-processing steps that we have just discussed, like tokenization, stopword removal, stemming, and lemmatization. So I hope you are clear with this section and with this notebook. So now proceeding to section 2. In this, we will be So in this section 2, we will be seeing the text representation and the embedding techniques. In this, we have one hot encoding, bag of words, TF, IDF, and word to vec. In the previous section, before in the theoretical section, we have already discussed this techniques in detail, but just a quick overview of all these sections with the help of example. And the same example we will be using in hands-on. So before proceeding, there are some of the terminologies that we use in NLP. So the first is corpus. So it is actually the paragraph that we are using in the notebook. It is called corpus over here. So it is a collection of all the data lines and the data points that form a paragraph. So if you can see in this example, it contains many sentences, and this paragraph is called the corpus. And if we see the data lines over here, the sentences over here, like D1, it's morning walk, regular morning walk keeps one fit. So these lines or these sentences are called document over here in terms of NLP. The third is vocabulary. So it is a collection of all the unique words in the entire corpus. For example, dictionary has 10,000 unique words. So if you see in our example, the corpus, this is the entire corpus, that is a paragraph over here. And if we take the individual sentences from the paragraph, it becomes a document. And if we take all the unique words over in the sentences, it will become the vocabulary. So you can see the regular, morning, walk, keeps. These are all the vocabularies that are unique in the entire corpus. So our first text representation technique is one hot encoding. So this is a technique in which we are converting the categorical data into the numerical representation. So if you see in this example, this is the corpus, and that is the same example over there, and it has 4 documents. So if you see the vocabulary over here, there are 10, a total number of unique words are total number of 10 over here. So if you see over here, the one hot encoding representation will be a vector of 10 for each of the word. So now you can understand that why the vector is of 10 words, because the vocabulary consists of the 10 words over here. So there are unique words that will be representing, not encoding. So if you see in this example, the D1, that is the morning walk keeps fit, the total number of words in D1 are 4. So that is why the word created here will be a sparse matrix, and it is represented as a vector of 10 for individual words over here. Similarly, for D2, we are doing D3 and D4. So advantages is that like it is simple to implement, but some disadvantages will be like it forms a sparse matrix. So matrix is unfilled, and eventually the memory is also wasted. It may have out of vocabulary issue, so it cannot handle new data. So and the another disadvantage is that it is not of fixed size. So like D1 is of 4 size because it has 4 words, and D2 has 5 words, so that is of size 5. So it is not of fixed size. And the fourth disadvantages, the semantic meaning is also not captured over here. So that is the relationship is lost between the words. So now another technique is bag of words. Taking the same example, here we are calculating the frequency of the words coming up in the corpus. If we see in all the D1, D2, D3, and D4, morning is coming 2 times. So here the frequency is also captured over in bag of words. So if you see in this example, vocabulary, we have 10 words over here. And here it shows the frequency, like morning is coming 2 times, walk is coming 3 times, fit is coming 3 times. So if you see in the bag of words representation, for the word fit in D3, it is showing 2 times. That means in the sentence D3, the fit is coming 2 times. So this is the beauty of this technique, that it also captures the frequency of the word. One thing to be noted here is that before bag of words, lower casing is important to avoid the repetition of the word. And then it also has an option of binary bag of words. It binary means it present or not present. So just to make sure, we'll be seeing this in the hands-on session. So if you can see, it is a vector representation is given over here. And in this one, and in the D3, we can see the fit is coming 2 times. So vector represented here is, it is showing the frequency of the word also. So the advantages of this technique, it is simple to implement, and it captures the similarity between the words. But also the disadvantages are like it again creates a sparse matrix. It can show the out of vocabulary issue, and ordering of the words is completely changed over here. The third technique is term frequency and inverse document frequency. So here the term frequency in this, the more weightage is given to the rarely present word in the vocabulary. And in inverse document frequency, it captures the common words present in the document. So if you see this example, there are 4 documents over here. So n is equal to 4 over here. And after stopword removing the vocabulary, we have around 10 unique words over here. So we calculate the term frequency using this formula, that is term count in document divided by the total number of words in the document. So if you see example for the D1, that is morning walk keeps fit. In D1 there are 4 words. So for the word morning, it is coming 1 time. So the term frequency will be 1 divided by 4. And here the 4 comes from the number of words present in the document. Similarly, you can see for the word walk, keeps, and fit. If we see in the document 3, there are 4 words, and you can see that the word fit is coming 2 times over here. So the TF is calculated here as 2 divided by 4, and then it will be 0.5 over here. Similarly, we will calculate for all the other words, and we'll calculate the term frequency using this formula. The next is the IDF, that is inverse document frequency. Here we log of count of documents divided by the count of sentences containing the word. So if you see in this formula, the word keeps over here. So the document frequency is 1, that is, it is coming in only one document over here, and the IDF will be calculated over using with this formula. So you can, whenever you are performing any other sentences, you can use a calculator and then calculate it by yourself. We can see this, we will see this in the notebook. So now the IDF is the product of TF and the IDF that we have calculated. So if you can see in the D1 example, the morning, the TF calculated was 0.5 and the IDF was 0.301. So the TF IDF is the product of these two, coming up as 0.075. So if you can see the vector for D1, morning walks keep fit, it is giving for the 4 words over here. Similarly for the D2, D3 and D4, it will be calculated with the same formula. So now if we do the final interpretation of this technique, so the words appearing in many documents, like the word walk is coming, so it has low IDF, therefore low TF IDF. But the word appearing that is only in the one document, like the word body, delightful, it has high IDF and therefore high TF IDF. So that is words like which is appearing only one time, like body, mind, delightful. They are given importance in their respective documents. So advantages of this technique is that the importance of each word is captured and the semantic information is captured over here. And it also has some disadvantages like sparsity and out of vocabulary issue. So now if we see, that was the text representation techniques covered in the above section. In the word embedding, it is a technique to convert the vectors into embeddings. So it can be a sparse matrix or a dense matrix. So the sparse matrix techniques we have seen, like one hot encoding, bag of words, TF, IDF. What if we want to create dense matrix? So we use the word2vec, and the two architectures that are used in word2vec are continuous bag of words and skipgram. So if we see word2vec, we follow for some steps before performing the word2vec. If we see, these are the 4 documents over here. So step 1 will be text pre-processing. In this, we are going to convert it into lowercase and remove all the stop words. In the step 2, we are going to build the vocabulary to get all the unique words. In step number 3, we are going to decide the model type. So it has 2 architectures. One is the skipgram and the second is the continuous bag of words. So both of these architectures work in different ways. In skipgram, we predict the context from the target word, and in continuous bag of words, we predict the target from the context. So it will be more clear with an example over here. In step number 4, we are choosing the window size as 2. For example, if we take the window size 2 here, that means the 2 words before and after the particular word will be seen into it will be considered to create years. And then we are in step number 5, we are creating the training pairs over here. For example, if we are taking morning, walk, keeps fit, and if we take the architecture as skipgram, in which we are getting target, we are getting the context from the target. So for each word, we will create pair. If we take the target word as walk, the context word within the window of 2, like will be morning, keeps and fit. So the training pairs will be created as walk and morning, walk, keeps, walk, fit. So with the help of the target word, we are actually creating the pairs with the help of target and context over here. In the second architecture, we are creating the target from the context. So now the logic is completely reversed over here. So the contexts are morning, keeps, and fit. So the target will be walk. Now the training pair which has been created will be like the context over here, like morning, fit, and keeps, and the target created here will be like walk over here. In step number 6, we are creating the neural network structure. So the word2vec is actually a shallow neural network. Like the other neural networks, it also has an input layer, hidden layer, and the output layer. And step number 7, we are learning the word vectors. So during training, the model is going to adjust the weight, and the word appearing in the similar context will get the similar vectors over here. In step number 8, it is the output. That is, we are getting the word embeddings after training. Each word will get the dense vector over here. Now, if we see in the second notebook that I have just shared, so in this notebook, we are going to see the text representation and the embedding technique. In section 1, it is one hot encoding. To perform this technique, we are going to install the scikit-learn. If we are using Colab, it is usually installed, but if in case you are using Jupyter or on VS Studio, so you have to install this library. So from scikit-learn feature extraction.text, we are importing the count vectorizer, and then we are importing the pandas over here. We are taking the same example as discussed in the slide. We are going to define the document over here. This is D1, D2, D3, and D4. Here we are initializing one hot encoder vectorizer. So the count vectorizer, the stop words we are taking here as English, and we are selecting here binary equals to true. Using the fit.transform, using this function, we are passing the document and then creating the one hot vectorizer for this. Here in this step, we are creating the data frame in which we are getting the names out for the D1, D2, D3, and D4. And if you see in the display of this section, these are the vocabularies coming for all the documents. And this is the one hot encoding representation. This section is same as we have discussed in the slide. In this section, we are performing bag of words. This section is similar to the one hot encoding one. Just to keep in mind is that in this step where the count vectorizer is coming, in one hot encoding, we have selected binary equals to true. But in this step, we are keeping binary equals to false. That is a default one. So here in the one hot encoding, binary true means like whether the word is present or not present in the document. So similarly, using the fit transform function and passing all the document, we can see the vocabulary after the bag of words representation. You can see for the word fit over here in the document 3, it is coming for the 2 times. So if you have noticed in one hot encoding, if the word appears twice, still the value will be 1 over there. But in case of bag of words, if the word is appearing twice, the value will be changed to 2. So it actually considers the frequency of the word present in the document. In this section, we are performing TF-IDF. So we are going to import the function TF-IDF vectorizer over here and then pandas. Again, we are going to define the document and then create the vectorizer over here using the stop words of English. So if you want the raw TF-IDF without normalization, you can add norm equals to none in the brackets over here. So after transforming this document and converting it using the data frame over here, you can see in the display section over here. So these are the values calculated as we have discussed in the slides, the form using the formula TF and IDF separately. These are the products of TF and IDF coming up as the vector representation of each word over here. So now if you want to see the IDF value of each word in the for the words, it is passed up as a data frame as a dictionary of term and IDF over here. And the values are displayed here in the section over here. In section 4, we have two architectures over here, that is skipgram and continuous back of word. So we have already discussed that for skipgram, we are going to predict the context from the target word. And the second is the continuous back of word. So here we are going to predict the target from the context. So for this technique, we are going to import the library called Gensim. The second notebook is already shared in the chat. If you can just go and the second one, that is, it is shared. Please check. So our step one is we are defining. So in the step one, we are defining the paragraph over here. So it is a big paragraph, which is containing around 5 to 6 lines over here. And then in step 2, we are performing the pre-processing. It is the same step that we have discussed in the notebook 1. That is, we have lower casing and then removing all the punctuations. These all the steps are similar that are given in the notebook 1. So after performing all the pre-processing, the clean text will be like, it is lowercase and all the punctuation mark are removed over here. In step number 3, we are doing a tokenization of the paragraph over here. So using the NLTK tokenize, we are importing word tokenize and then downloading the additional package, that is the punk tab over here. So now the tokens are the word tokenize of the text passed on over here. And if you see in the display section of this, all the words, all the unique words are present over in this section. In step number 4, we are preparing sentences for the word to vec. So now all the tokens, we are passing it as a sentence over here. In step number 5, it is divided into two steps. The step 5.1, we are going to train the skipgram model over here. And in step 5.2, we are going to train the continuous back of word model over here. So from the GenSim models, we are going to import word to vec. So this word to vec is used to convert the words into the numerical vectors over here. Now, training this skipgram model, we are passing the word to vec and we are passing the 5 parameters over here, in which the first is the sentences, that is the input training data. So there's a list of all the tokenized sentences that we have given up in the paragraph on the top. So for example, the morning walk, keeps, word, this is one document, tokenized form of one document. And the second in the second parameter, it is a vector size. So the dimensionality of each vector will be of 50. Now it will be represented as a vector of 50 numbers. In the third parameter, it is a window of size 3. So that means the model will look at the 3 words before and 3 words after the target word to learn the relationship between the words over here. A minimum count is kept as 1, that is the minimum frequency threshold. So that means the word appearing less than this count will be ignored. So here keeping 1 is that we are going to include all the words present in the corpus. And now SG equals to 1. That means we are going to keep the skipgram equals to 1. So now if we keep it as 1, that means we are training the skipgram model. And if we are keeping it as 0, that is we are going to train the continuous bag of words model. So in this step, we have successfully trained the skipgram model. And this 5.2 step, just keeping the SG equal to 0, we are going to train the continuous bag of word model over here. In step number 6, we are going to find the similar word. To find the words mostly similar to the word economy over here, it is based on the word embeddings that is learned using the word to vec skipgram model. So now if we see, we are going to we are finding the similar words related to word economy. So to get in this step, to get all the words, we are using the function most similar over here and then passing the word that we want to compare with. And if we want that to get the top n results, we can add the option top n equal to 5 or 6 or whatever number you want to select for this section. Similarly, the word embeddings learned from the continuous back of word model similar to the word economy are represented over here. If you see in the value, there are minor changes in the value size because both the model are trained differently. So the answer coming are slightly different from each other. In step number 7, we are calculating the cosine similarity between the two words. So here the function similarity, we are going to compute the cosine similarity between the vector representation of the two words. So for example, we are going to see the similarity between the two words, that is economy and agriculture. So using the function similarity and passing both the words over here, we can see that how the economy and the word agriculture are related. Sorry, the words India I have taken up over here for the example. So you can see in the word economy and India, they are correlated by this value. And in the second step, that is in the continuous bag of word, it is given as this value. So if you have noticed in the skipgram, it works better for the rare words and it captures semantic relationship slightly better than the continuous bag of word. But whereas the continuous bag of word, the training is very fast and it is good for frequent words. So now the difference comes from the how both the models are trained. So these step is similar from that we have discussed in the slide. So if we summarize this entire concept in one line, the skipgram focuses on learning the context relationship for each word, which helps the rare word and the semantic understanding, while the continuous bag of word averages the context information and make it computationally faster and efficient for frequent words. In this step, we are visualizing both the vector representation. So using the matplotlib, we are plotting the graphs over here. With the help of PCA, we are reducing the dimensionality from 50 dimension to 2-dimensional over here and visualizing it as a graph over here. So if you can see by plotting both the plots side by side, the plot 1 and plot 2, the visual representation will be like this. If you can notice, both the plots are almost similar because here we are using a very small paragraph and we are using the similar kind of words over in both of them. So with this, we come to the end of our section second. I hope this topic is clear with the help of the hands-on as well as with the slide. Okay. So now proceeding with section 3, here we will be combining all the techniques that we have discussed in section 1 and section 2. So we will proceed. We can have a break of 5 minutes and then we will proceed and see the end-to-end line of the NLP application that is applicable to all the applications you want to proceed. So are we good to resume the session? Shall I continue? Okay.
Yes,
So
ma'am.
in this section, we are okay. In this section, we are going to see the end-to-end pipeline of NLP application. So for the demo purpose, we will be seeing a spam classification application over here. So again, we are the steps that we will be following over here are the text pre-processing using the library NLTK. And this the steps that we have discussed in the notebook one. We will be performing that. And then in the second step, we will be doing all the text embeddings that we have discussed in the notebook two. So here, it is not necessary to use all the techniques at the same time. But for the demo purpose, we will be doing it in the separate section so that we can compare all of them. But for your application and for your use case, you can use any one of them. And the third we will be doing is the classification. For now, we will be using the logistic regression over here, but for your use case, you can use a nice base, SVM, decision tree, whatever suits your use case over here. So if we go to the notebook 3, so any end-to-end NLP pipeline, in this, the steps that we will always be performing is the text pre-processing and then text embeddings. We're using any of these techniques or the combination of them. And then third will be, we will be using the machine learning or deep learning model to train a model over here. So in this step, we will be splitting our data set into train and test, and then we will be selecting the model. We will train a model and then eventually evaluate the model using the accuracy or other metrics over here. So now we have to install all the NLTK, all the libraries like NLTK, scikit-learn, gensim, and matplotlib. So one of you have the doubt that you were not able to download the NLTK or their name error is coming. So make sure you are using this step before running or importing any other library over here. So here the NLTK is used for text pre-processing and NLP tasks. The scikit-learn library, that is a machine learning library over here. The gensim is an advanced text representation and topic modeling library. And the matplotlib is for data visualization. So step one is to import all the libraries, pandas for handling data sets, numpy for numerical operations and array handling, RE that is for the regular expressions that we will be using at the time of text pre-processing, NLTK for all the NLP tasks, the matplotlib.pyplot for plotting graphs and visualizations. So like from the nltk.corpus, we are also going to import the stop words over here. That is to remove all the common words. And then we will be using nltk.tokenize to import the word tokenize over here. So this function will be used to split the text into individual words. Similarly, from the nltk.stem, we are going to import the Porter stemmer and the word net limitizer for stemming and limitization purpose. So all these libraries are used to perform the text pre-processing part. Now from the scikit-learn.model selection, we are going to import the trained test split and cross-validation score. This is for splitting the data set and performing the cross-validation. For a demonstration purpose, we will be using the logistic regression. So for that, we are going to import from .linear model logistic regression. And you can also try with the knife Bayes classifier and other classifiers if you want to. And then from the metrics library, we are going to import the classification report and the accuracy score to evaluate the metrics and evaluate the model over here. From scikit-learn, the feature extraction.txt, we are going to import the count vectorizer and tf-idf vectorizer. So the count vectorizer is for creating the one-hot encoding if we are keeping binary equal to true. And similarly, the codes are all same for the bag of words, just we make sure to keep the binary equal to false over there. And from the gensim.models, we are going to import the word2vec. This is for creating the word embeddings over here. So after importing all the important libraries and the methods present in these libraries, we are going to download some NLTK additional resources. The first is the punct, that is for the text and the word tokenization. And punct tab also is an additional resource that we will be needing. And then we will have to download the stopwords and wordnet. These are steps similar. If you follow the notebook 1 and 2 sincerely, you will be able to understand all these steps. So in this step, we are downloading an SMS spam dataset from the UCI machine learning repository using the command line tool that is from wget. We are going to download it from the internet as a compressed zip file. So the syntax of this function is like wget, and we are going to give the URL of the file that we want to copy. So here the zip file is downloaded, and then we will be extracting or unzipping the downloaded zip file so that the data set can be accessed. In step number 4, we are actually loading the data set. After downloading it as a zip and unzipping it and extracting all the data set over from there, we are going to load the SMS spam dataset into pandas data frame using the separator as a tab. It specifies that the file is actually tab separated values. So the names are as a list of labels and text and assign it to column names to the dataset. So with the help of the pandas read CSV function, we are going to read the file, that is the CSV file over here. You can see the heading, the label, and the text. It is given in the here in the data set in the CSV file over here. So now we are going to convert the text tables into the numerical values for the machine learning models. So we are selecting 0 for not spam and 1 for spam messages over here. So if you see the data frame in the display section, the column are given label, and then we are having a mapping of ham or spam over here. So here the 0 represents ham and here the 1 represents spam over here. With the help of a head function, we are just displaying the top 5 rows for the dataset. In step number 5, we are performing all the text pre-processing as discussed in notebook 1. Here we are cleaning, tokenizing, removing all the stop word, stemming, and lemmatizing. So we are going to create a set of English stop words to using a set to improve the lookup speed while filtering the words. So we are creating the set of these stop words in English and then initializing the POTA stemmer object. Similarly, for the wordnet limitizer, we are initializing it over here. And in this function called preprocess, which is taking the text as parameter, we are converting it all the text into lowercase, and we are removing all the punctuation marks with passing this as a regular expression over here. And then we are tokenizing all the text into individual words with the help of the function word tokenized. Similarly, we are stemming and lemmatizing all the words present in the words and then we are applying the pre-processing function to every text message in the data set. So the result is now stored in as a new column called the clean text over here. If you see in the display section, clean text, this column is actually representing all the text after the pre-processing has been done. So now this is a step that we use for training all the machine learning and deep learning models, that we are splitting the data set into the training and testing set. So now using the function train test split, we are splitting the data set in the ratio of 70 to 30. You can make it 80, 20 or 60, whatever, 40, whatever suits your use case. And then we are fixing the random state, or that is a seed, the training purpose as 42 over here to generate the same values every time we run the or train the model over here. So these are the 4 sections over here. That is one hot encoding, bag of words, TF, IDF, and word to vec. So we will be doing training the model using all the 4 techniques, and then for the comparison purpose, we will check the accuracy. So in the section 1, if we choose one hot encoding, we are going to create the count vectorizer object for one hot encoding. Here we are keeping binary equals to true. That means we are recording whether the word is present or not present in the corpus. So now we are converting it into the clean text into one hot encoding feature matrix using the function fit transform over here. Function will learn the vocabulary and transform the text into vectors over here. So now we will be initializing the logistic regression model, keeping the max iterations as 1000 over here. So increasing the maximum iterations will be used for convergence purpose. And here we are performing the 5-fold cross validation to evaluate the model. So now the data set is split into 5 parts and the model is trained and tested 5 times over here. And after deciding the accuracy and shape of the feature matrix, the accuracy is coming up here as 0.9793, and the shape of the matrix, feature matrix, is given up over here. Following the same steps, if we are going to do with the bag of words, keeping the binary equals to false as discussed in the notebook 2, we can see the accuracy of this is also similar to the one hot encoding one. But when you will be training it using a big data set and different data sets, the accuracy will differ automatically. In section 3, we are going to perform the TF-IDF. So using the TF-IDF vectorizer and the function fit transform, we are going to build the vocabulary and convert it into the numeric vectors. Again, we are going to initialize the logistic regression models, keeping the max iteration as 1000 over here. And we will follow the same steps, like we are going to perform the 5-fold cross validation and then calculate the accuracy. And the section 4, we are again going to do repeat the same step, keeping the word vectorizer over here, in which if we see word to vec model on the tokenized sentence, we are passing the sentences, that is a training corpus, keeping the vector size as 100, that is the dimension of each word vector, keeping the window as 5. That means 5 words before and after will be considered, and keeping the minimum count as 2. That means the model has to ignore the words that appears less than 2 times over here. Similarly, here we are going to initialize the classification model, that is the logistic regression, and then perform the 5-fold cross validation and calculate the accuracy over here. So now after performing all these 4 sections, if we see in the observation, if we see in the display, that is a sparse matrix has been created in the first one, and in the second one, that is a dense vector representation that is created as a word embeddings after creating from the word to vec. So now to demonstrate the semantic similarity, the advantages here is already given up over here. Like if we consider the word free over here, so this represents that how word similar, a mobile word is similar to the word free over here, and similarly for the tone. So if you do the final comparison summary, in the one hot encoding, bag of words, TF-IDF, they are giving the sparse matrix and the meaning of the word captured over here. But in word to vec, it is dense and but the meaning of the word is being captured. So eventually the accuracy here is coming low in comparison to others. But whenever we're using another data set or train using another machine learning algorithm, it might vary. So this is the end of the end-to-end NLP pipeline. Please try it, and you can also do this assignment of your own. You can download any publicly available data set and then follow all the steps given in the notebook, that is text preprocessing. You can apply different text vectorization techniques, and you can use any of the machine learning model for classification and then compare and analyze the result that you get after the training the model. So some examples that you can perform or the ideas you can do is semantic analysis. In this, the sentiment analysis, sorry. In this, the sentiment will be like positive, negative, neutral. And another example can be fake news detection, where the news can be classified as fake or real. Another example can be topic classification, where the news or any editorial can be classified as sports, politics, technology, or business. And another thing can be an email classification that in that you can like classify your mail as work, promotions, social updates. So there are many more examples that can be performed using the same pipeline. So with this, we come to the end of this session. I hope you have understood all this and you will try the notebooks of your own.
Participants, if you have any question, please go ahead.
Please let me know.
I think there is no more question from the participants, ma'am.
ग्राउंड फ्लोर में हमारा ऑफिस है उसमें तुम उसको बोल दो उधर वो ही बैठेगी और कोई नहीं बैठे और ग्राउंड फ्लोर में
Hello.
हेलो हमारा टीम
Yeah.
उसमें बैठेंगे बोलो
Thank you very much, ma'am, for your wonderful and insightful session on word embeddings and text representation technique. The concepts were explained in a very clear and engaging manner, and the hands-on practical demonstration helped us understand their real-world implementation much better. On behalf of Dr. Vaska Mandal sir and Dr. Mukesh Kumar sir, I extend our sincere gratitude to you for taking the time to share your valuable knowledge, expertise, and practical insights with all of us. We truly appreciate your efforts in making this session informative, interactive, and enriching. Once again, thank you, ma'am, for your wonderful session. We look forward to learning from you again in future. Thank you, ma'am.
So if participants would like to say something, something else is needed in future or right now, we are ready to help. Thank you so much, Sushmita. If anyone would like to speak
Hello.
from the participant side.
Hello.
Someone is saying, I'm not
Somebody-
able to hear. I'm
Am I
not sure.
audible, ma'am?
Yeah. Yes, sir.
This is
Yes,
Sachin.
Bataiye. Yes, please.
Ma'am, I have a question related to this text analysis. Basically, we are using some paper for a literature review. Is there any technique by which we can design a literature review with the help of this text analysis through NLP?
You want to say some AI tool?
Yeah, ma'am.
No. Actually, I don't even know, and we don't prefer students to do it. They can do it their own, and later they can have some tool so that they can verify what has been done is good or not. So far, I'm not aware of such kind of tool. Using the text analysis can be done. Actually, what my students are doing, they are reading the papers using the Google scholars. They find the best in the area, and later they can take the help from AI tools. Those are available nowadays widely, and they are good, so that they can verify what they have done and what is right. So that way they don't lose their creativity. But I'm not aware of such kind of tools.
Thank you.
So we can conclude the session. Can I exit? So Shweta, if no one is
Yeah,
having any
yes,
questions.
ma'am. Yes, and you can.
So we have shared everything with the participants. They can practice at home.
Yeah, one more question in chat box, ma'am.
So actually the question is contextual word embedding work. So basically that is kind of a model. You understand it like that. So if I say the cat sat on the mat, right? So if the question mark on the mat. So we need to find what is there. So cat and mat has got some kind of corpus in the, some kind of sentences in the corpus, right? So means some model is needed for that. LSTM is one of them. There may be other models as well. So we have to have a training kind of thing. We have to make some kind of mapping with the cat and mat in this example. Currently, the cat and mat is having a context behind sitting. We'll be able to find the sit. This is one example. There are several, right? So again, that's a different topic. And of course, we have to have some kind of modeling that is available. Any other question? And we enjoyed your participation. Many questions, many appreciations. We thank you, Roji, then Abhishek, Rana, Sachin, thank you so much. And Padmavati, Ketan, Jethani, everyone is, I'm thanking you.
Session will be start on 4 p.m. Please just stay connected.
Not audible.
Participants, please wait for 5 minutes. Session will start shortly. Good evening to all the participants. Now we have the session, hands-on session of Dr. Mukesh Kumar sir. He is an assistant professor in the Department of Computer Science and Engineering at the National Institute of Technology, Patna. Sir, having more than 9 years of experience in academia and industry. Sir obtained his PhD in Computer Science and Engineering from NIT Rourkela. His research interests include artificial intelligence, machine learning, deep learning, big data analytics, recommender system, and medical image analysis. He has published several research papers in reputed journals and conferences, and he is actively involved in teaching research. And today, sir will take a hands-on session on autoencoder, variational autoencoder. This practical session will provide participants with an opportunity to understand the concept along with their implementation. With this brief introduction, I warmly welcome Dr. Mukesh Kumar sir and request him to kindly take over the session. It is visible, sir. Anupam sir, you can share your slides.
Yeah, right now I share the screen. Is my screen visible?
Yes, sir, it is visible.
Okay, so so in this session we'll be seeing about autoencoder, why we use and why we need autoencoders, what is the architecture and why, what is the various types of autoencoders, and or we can say that what is different variation of autoencoders, and what are the loss function used when we use autoencoders, and what are its advantage, limitation, and practical application. So first of all, autoencoders, you can see that an autoencoder is simply a neural network that learns to reproduce its input at the output. Unlike you can see different classification models that predict labels, an autoencoder, besides an autoencoder receives data such as an image or feature vector, and it compresses it into a smaller representation called as the latent space, and then reconstruct it to the original input. During the training, the model is not given the labels if we are dealing with the supervised algorithm, so it doesn't given any label. Instead, it learns by minimizing the difference between the original input and the reconstructed output. This makes autoencoder a form of self-supervised, or we can say, or unsupervised representation learning. So this is the basic of autoencoders. So why we need autoencoders? So many real-world data set contains redundant information. So autoencoders learn compact representation that preserves the most information while discarding redundancy and noise. They are widely used for, we can say, for dimensionality reduction, denoising, and anomaly detection, image compression, feature extraction, recommendation system, medical imaging, and data visualization. So these are the area where we can use autoencoders. So there are different types of autoencoders. We can say vanilla autoencoder. This is a basic encoder decoder architecture. The second one is sparse autoencoder. You use sparsity, so only a few neurons are active in that sparse autoencoder. Denoising autoencoder, it learns to reconstruct clean data from the noisy input. Contrastive autoencoders, it adds a regularization term to make the latent representation robust. Deep autoencoder use multiple hidden layers to learn complex features. Convolution autoencoder use convolution layer for image data. This is basically for CNN and image data. Recurrent autoencoder use RNN, LSTM, and GRU. They are just basically for the sequential data. And the nowadays we use that is variational autoencoder. It learns a probability distribution in latent space, enabling data generation. So it is when we will be seeing autoencoder, there is a next step to generate synthetic samples from the given data set. So we use after variational autoencoder, there is a concept called GAN, and generative adversarial network, that is used to generate as the genetic synthetic samples from the given data set. So in this particular practical session, we will be seeing a shallow, a deep, sparse, and denoising autoencoder. So as you can see, shallow autoencoder, or we can call it as a basic autoencoder. There is only one encoder and one decoder, and second one is deep autoencoder or CNN based autoencoder, that it has multiple encoder with multiple decoder. We can have many to many relationship. There's many encoder and many decoder. A sparse autoencoder, that it uses sparse means it uses as we can already see, already I have told that sparse is generally only few neurons were active during this. Denoising autoencoder, that we add some noise with, that is called Gaussian noise, and we try to with encoder we try to encode some noise, and decoder is what it is responsible to decode noise and give us the original image that was that was before noise. So for particular this particular autoencoder session, we will be using TensorFlow instead of PyTorch. So if you don't have TensorFlow, you need to pip install it, and for particular installing any particular package, you need to have following command: pip install TensorFlow. If you want, if this statement will download the latest version of TensorFlow. If you want to have a specific version of TensorFlow, you need to specify with a double equal to that I want to download the particular TensorFlow version. So these NumPy and Matplotlib, these are basically NumPy packages, and this is used for plotting any data or these things. So if TensorFlow is already installed, so we can import it as with the alias name. For this particular autoencoder session, we will be using MNIST dataset. It is a fashion dataset containing of 10 classes, and for designing layers, we will be using dense, and dense will be the hidden layers, and input will be the input layer, and keras.model will be from that we will importing models. So if you run this, if it is already by default, Google Collaboratory have NumPy and Matplotlib by default installed. So I think all of the packages might be default installed. If not, you can just check it if it is installed or not. So then we will be loading, since Keras has some of the predefined data set that it already have. So Keras have MNIST data set. So this MNIST data set have already have its own classification. It is already divided into trend test. So we don't need to have we don't need to do further classification of which portion of the data is trend, which portion of the data is test. So so it what it this MNIST data have, it loads what particular this code does. It loads 60,000 training images and 10,000 test images of handwritten digits, that is from 0 to 9, and there are the two processing steps matter here. These two processing steps these two processing steps matter here. It scales the pixel value from 0 to 255 down to 0 to 1. So network generally train better on small numbers, and this is what this thing is done, and then it reshapes, and or we can say reshape flatten each, because each image is a 20 crate cross 28 into a one row, that is 784, because a plain dense layer expect a flat list of number rather than a 2D grid, so if we print the train and test step, we can see training has 60,000 images and the testing has 10,000 images. So now we will be seeing, yes. So now we will be seeing, so now we will be seeing shallow autoencoder or basic autoencoder. So what it does, this is the simplest possible autoencoder. Means one layer to encode and one layer to decode. Input defines here the input shape, that is 784 pixel value, and the dense, it defines the dense 64 is the encoder. It flattens 784 number down to 64, and this dense 784 sigmoid is the decoder. It expands those 64 number back to 784 using sigmoid activation function, and because pixel values live between 0 to 1, model wires the input and output together, and this input and output together into a trainable network, and then compile and set Adam as the optimizer and binary cross entropy as the loss. And this binary cross entropy, because it is this MNIST data, this handwritten data is basically given a particular image. It is the if it is a 9-digit image or not. So it's a binary class. So we uses loss as a binary cross entropy. And for seeing the model summary, we can see just you need to type the summary function for the given design model. So this is how we can see the input layer has 784, because we need first all the 784 flatten squeezes image, then it downsamples to 64. This is the encoder part. Then this dense is encoder part, and this dense one is the decoder part. Now we will now we will what uh, we will do. This is, you can say, this is the key line in the notebook, that the input and the target are both extreme. The network is being asked to reproduce its own input. That is the entire definition of an autoencoder in one line of code. So just we want this is the simplest autoencoder, so we don't add anything extra to it. So what we give, with the same image we give, the same image we want. So this is the key line for this particular cell. Now since for the shortage of time, I have run the model till 5 epochs. Batch size is 256, and Safal is true that there is no overfitting of the model, and the validation data is same as X-test, because this is simplest autoencoder. So how we can see this is particular code to see what is the image means the first image is shown. Since we train the model, now we predict the model by giving the X state. So now we will plot the figure with this is what is the encoder part. Means this is what the encoder has got image first row 7204 digit, and this is what decoder has generated. So this is how we can see it visually, that this particular first row is the image that is getting that has got for the encoder. This is how a decoder has decoded this particular image. So since you can say it is a trivial task that giving the same image and generating the same images. So since it is a basic autoencoder, since there is a one encoder, there is a one encoder and one decoder, so is we also say it is a vanilla autoencoder. Now next thing we will be seeing is deep autoencoder. In deep autoencoder, we will be using same overall idea as the solo version, but with several layers on each side. So instead of 784 to 64, we first given input shape as 784, then downgrade to 256, then again 128, then again to 64. So this is what this encoder dense this particular code is what is the latent representation of the given particular image that is passed through encoder. So this is what this is called as a latent space. So it contains all the relevant information in a compressed format. So we call it as a latent representation. Now from this part to above, all the part was related to encoder. It just basically bottleneck the representation to a latent representation. Now again we want to reconstruct the data from the given latent representation. So again we upsample it. So from 64 we go to 128, then we go to 256, and then we go to 784. And the same thing we use. So why? So one many of you can ask that why extra layers. So the extra layers gives the network more capacity to learn richer and hierarchical features. Earlier layers tend to capture means not only the simple patterns they capture, but deep layers capture finer details. So reconstruct typically looks sharper than the shallow version. So this the image that is provided. You can see there is exact image, but this reconstructed image is not as it seems to be some blurry type image. So for deep autoencoder, the number by increasing number of layers, we can say that the we can learn higher or richer and hierarchical features. So this is how we can see the model summary. As the number of layers increase, so number of trainable parameters also increases. So same thing here, we since the same image we want to give to encoder and the same image we want from, so image will be the same extend, and will be the video for all the autoencoders, since this will be same. Now we can, since for the shortage of time, I have trained till 5 epochs only. Now we can see the what is the image taken by the encoder and what is the image that is generated by the decoder. We can see here that the image taken by encoder as compared to the decoder side of shallow auto encoder and decoder side of deep auto encoder, the image the image that generated by the deep auto encoder by decoder part is more sharper than we can say it in the previous basic auto encoder. So this is what we can see by adding the layers. We'll try to learn more extra features or more rich features than the basic auto encoder fails to learn. So this is the idea for by adding a number of layers to by adding number of layers. So we call it as deep. So it has many number of layers as compared to solo encoder. Now we will be seeing another type of autoencoder, that is a sparse autoencoder. So for a sparse autoencoder, the same architecture as the shallow autoencoder, but one addition. Here the here activity, here you can see this activity regularization is equal to regularizers dot 114. This penalizes the network for having too many active neurons in the bottleneck at once, so encouraging it to represent each image using only a handful of active units rather than all of 64. Means what I'm saying, that instead of using all the neurons, instead of using uh, uh, instead of activating all the neurons, we will be activating all the neurons in the or sparse means what in the basic term can see dense means, or if you see a dense matrix, in dense matrix of 0 and 1, we can see the matrix is called dense matrix when all the values of dense matrix is 1, and a sparse matrix is what, that some value have 1, some value have 0. So you can apply 1 0 is at 1 0 is to 1 0 represents as deactive and 1 represent to active. So sparse means some of the neurons will be active and some of the neurons will be deactive. So this is the whole and soul architecture, whole and soul idea of sparse autoencoder, that that it that it encourages it to represent each image using only a handful of active units rather than all of 64. So one of may you ask, sir, which of the neurons we can make active and which of the neurons we can make deactive? So it's again hyperparameter. It depends upon by programming or reading the research paper of autoencoder, will be seeing that which portion of the neurons will be get active and which portion of the neurons will get deactive. So you can see the result tend to be here when we will be seeing what is the image that is generated by the decoder, how it make different from other two autoencoder. So this is the what we will be using same concept, but we will be taking one more argument here. It is same as the basic autoencoder, but here we added one attribute, that is activity regularizer equal to regularizer dot L1. So we penalizes some of the neurons with L1 regularization with with learning rate is one, we can say 0.001, and this is what we can write 1e minus 4. Now this is the total parameter that is learned during this parse autoencoder. Now, same thing we will be training for the model till 5 epochs, and now we can see that means when we active some of the neurons and we deactive some of the neurons, the quality of image also degrade by much extent, because the architecture is same as basic autoencoder. But here, since we penalizes with regularizer L1, so the means most of the means this particular data set, that is MNIST handwritten data set, the image quality uh, means basically drops, but it we can't differentiate between what encoder has got and what decoder has generated. So all the images are looking in the decoder part are looking like same, but in encoder part they all are different, but in decoder part all in the same. But so that's why I have told that what to how many time you have to penalize, and with how many time you have to not penalize. It depends upon how we I mean, it depends upon the requirement, or it depends upon the data set. But means what is the important? By adding noise, it can make model more more generalizable, or it somehow makes the model underfit. So it depends upon your choice and your data set requirements. So I just want to make familiar about you what the sparse autoencoder does. Now next thing we will be seeing autoencoder, that is denoising autoencoder. So in denoising autoencoder, we deliberately corrupts the image by adding some random, or that is called Gaussian noise, and then clips pixel value back into the valid 0 1 range, so they look like just like a means just like a blurry image. So we denoise with the factor 0.5, and we add all the image in the training part with adding that much of noise, and we also add with same with text, and we clip this what we have said, that then pixel are clipped back values back into the valid. So for make it since it is between 0 to 255, so make it, so I make it to 0 to 1. Now same thing what we have done denoising, since we have taken input step, since image is 28 cross 28, so we have taken 784, we have just squeezes it out to a simple 1D vector. So 784, then it downgraded to 128, then 64. This is what I have told earlier, that this is what the latent representation of the image. And again we start reconstruction of the same image from that latent space. Now again 128, now again 784, now again this is so here what we have done, when this is what we have this is how we can, this is same as what all the autoencoder have. If you want to wish, we can add more layers. If you don't want to, don't. So now here is for denoising autoencoder is a trick. This is a practical or interesting twist. The input and target are now different. You can say till from now to all the encoder that I have demonstrated earlier, all the training and the training and or we can say the input and target were the same. But here is the practical interesting twist, that the input and the target are now different. Noisy image goes in and clean image is expected. So we want that the encoder will encode some noise on the image, and the decoder has to denoise that image and give us the clean image. So to succeed at this, the network is forced to learn what is genuine signal versus what is noise. So we want our autoencoder to learn that what is the genuine pixel, and what is the noisy pixel. So given it, so for this problem, so given it a noisy digit afterwards, it and it outputs a cleaned up version. So we will give a digit which will be adding some noise that I already explained, that we will be adding noise of factor 0.5, and the cleanup version is what we call as denoising. So after adding noise, the decoder had to denoise it. So its name is its name is corresponding to its work, that it denoise the image. So this is how. So this is the twist for the autoencoder. Now we can see what we have seen till from the earlier autoencoder, that this decoded this so this 1 minute. So this encoder will add some noise to the image, and the decoder will the decoder will remove the noise from the image, and it will give us the uh, means denoised image of the given input. If the input has if we add a noise, so there is a twist, that if suppose take a real life example, that if we try to take an exam of take an exam of a student, and if we are more smart enough to that more smart enough that if we set a question like that, nobody can cheat. So this is what is difference between real and fake. Suppose the noise is, we can say, the fake, and the denoise is called real. So this is we can this autoencoder can also helps to identify that which is the real image, what is the fake image. So this is the always, there is a rat and mouse of encoder and decoder, that encoder always try to fool the decoder, but it is the decoder smartness that it how identify its encoder, what it cheats, and and it decodes and it decodes what encoder that encodes it. So for basic, all since for the basic summary for each variant, that's all we can say. For each cell, suppose for shallow, the basic it is basic, compress, and rebuild one layer each way. And for deep, there are more layers, richer features, and sharper reconstruction. And for sparse autoencoder, it forces the network to use only a few or active features at once, and denoising it trained to filter out noise on purpose, noisy in and clean out. So now we will see the different types. Since I have not mentioned here, since I this is uh, this particular data set is related to binary classification. So I have used here binary cross entropy. So there are many loss function we can use. We can also use mean squared error for most common for continuous value data. It penalizes large reconstruction errors. We can also use mean absolute error. It is more averse to outlier than MSE. So for outlier, if there are more outliers in our data set, we can use MAE. Since we have used binary cross entropy, so it is suitable when inputs are normalized to the range 0 and 1, or we can say it is a binary classification. Huber loss, it combines both MSE and MAE. The KL divergence law, it used with variational autoencoders to regularize with latent distribution. Perceptual loss, we can use this loss to compare high level image. And there are many loss. Adversarial loss, when adversarial loss is when we use autoencoder are combined with GAN. So if we use autoencoder with GAN, we use adversarial loss. So what are the what are the advantage of using autoencoder? So autoencoder learn features without labels. We don't specify labels. It reduces dimensionality. It also compresses data, and it removes noise. We can see with the help of denoising autoencoder. It also supports anomaly detection and provide meaningful representation for downstream machine learning tasks. And what is the basic limitation of autoencoder? That it may reconstruct. It sometimes happen that it may reconstruct poorly if the bottleneck, or we can say latent representation, is too small, or may memorize data if it is too large. So it requires careful tuning of architecture and hyperparameters. And standard autoencoders are not inherently generative. So we need to have idea, or we can say limitation, when we will be using autoencoders. So now, what is the practical application that it uses image compression, image denoising. We can also use it in the fraud detection or medical image analysis recommendation system, or anomaly detection and feature extraction. Or if we do classification, we can also use this autoencoder as a feature extraction just before classification. So this is how autoencoder use. So basically I have used only so what you can do from this hands-on session, that you try to use these all types of autoencoders onto a data set which has large number of images, or we can say you can also apply on that images that have many classes. Since I have applied to since it is a bandit class, so by taking this session you can apply to a class, means multiple image data set that have, suppose, medical image, that to identify whether a given image is means you know, give the noisy image and you try to pluck it out with the correct image. So this is what you can do as a homework exercise. This is all from my side. If you have any doubt, you can ask question.
There is few question in the chat box, sir. Anukul sir,
Yes, I am seeing.
I think there is 2 or 3 question in the chat box.
Sir, can I 1 minute? Sir, I can give output of a sparse autoencoder. Yeah, you can give, but uh, but but I don't think this works. This work will be better if means sparse autoencoder is suitable where when there are, suppose when your so when you have some low resource application and you want your mm, work to be uh, more done quickly, so you sparse autoencoder, since you can say you can yes, you can feed the output of a sparse autoencoder into it is.
Hello. Hello. Hello.
Yes sir, you are audible.
अभी आवाज आ रही है?
हाँ सर.
अनुकूल नहीं है क्या?
यस सर, वो है.
Okay, so I think the question is how to use with text data, right? So I think in the first layer we can embed this text data, means in embedding layer. After getting the embedding, we can means add some extra layers and then reduce to, means in encoder part we reduce the dimension of that text, and then during decoder parts we can decode in the same manner. So embedding layer is the key component there. So suppose we are embedding with CNN, the text embedding with CNN. So just we means in one D filter we can use on the each sentence, and we can embed using CNN, and then in next layer in a similar way. After that we can continue with the code. I think this is clear. So we can also means can I share my screen?
Yeah, it
Is
is
allowed.
visible, sir.
So we can see different applications of autoencoders like super resolutions, denoising kind of thing. And in variational autoencoders, we can means get the embedding or latent space in such a manner that we can use decoder as a generator, right? So like we can means our loss functions will be based on the generation reconstruction loss and KL divergence, where different samples we can get the means how our probabilistic samples is similar or not. Susmita,
Yes, sir. Yes, sir.
अभी शेयर कर सकते हैं?
I'm making a presenter.
Okay.
Yes, sir. Now you can share your screen.
So, my code is visible.
Yes, sir. It is visible.
Okay, so as we have seen, this is the autoencoder, basic autoencoders, where we have some layers. Suppose we have used MNIST digit data set, and then after running this, we can decode in the same manner so that we can generate the code. Suppose we want to use that encoder parts or some after means this autoencoder we can use as a feature extraction part, right? So we can use in the latent space that latent features we can use for the further analysis. Like in these examples, we can see after training with autoencoders, we have a reduced feature, and that reduced features we can use. After that, we can use random forest to classify the things. Okay. So in these examples, you can see a simple single layer fully connected autoencoder that compresses that images into 32 pixel vector. So using means for in the case of means feature extraction part, we from 768 to 32 features we have extracted here. Okay, so during and this at this layer 32 layer, okay, that representation we can use for further analysis. So after that we have added the random forest head to classify the things, right? So if we run this code, so I think, okay. So here you can see the same code here we have, but we have loaded the MNIST data set where the image size is 28 cross 23, and we have this much of dimension. We have this model. So this is we have defined in encoder things. We have a linear models where we 768 features we will give as an input, and then in hidden layers we have initialized with in hidden layer I think this one 32. Okay. So it will reduce that dimension to this dimension, and then in the quarter parts from 32 to 768 we try to achieve. Okay, so during this reconstruction we learn some representation where all the images can be represented in the form of means 32 with 32 features, right? And after building this network and after training, here you can see we have used optimizer, and then we can use binary cross entropy loss, where our aim is to means generate or take the loss between cross entropy between the original image and the reconstructed image, and we try to reduce that things. So after that, after training, we can see what is the cause and during the backside of this one. So after training of this network, we can use and evaluating this, we can simply use, see, wait. Okay. Then we can use a training data set evaluation of this set. So you can see here, this is the output generated from the original to latent space. Okay. And then after testing, so this is simply we are training our encoder model. Okay. And after encoding, after doing this thing, next one is we have to use the reduced dimension feature or representation, and then we can use on the top of that we can use random forest. Okay, so here you can see. So this is based on the original feature, means what is the strand. Okay. Then after reducing the features with PCA, directly we will go with that one, encoder decoder part. So here we have loaded the training data set, and then we have compressed here. What we have done here, this encoder model, the output of encoder model we have stored in decoded part, and this decoded part of that features we have stored in extreme compressed, right? And corresponding to that we have stored the label of that image, means that thing. Okay, and then we can use this thing, this data set on the random forest. So in random forest classifier you can see here, so you can see here in random forest we have given extreme compressed data set that is generated from the encoded part. Okay, and then by training means the level of that data is given here, and then based on that random forest will generate the result. So this encoder can be used as a feature extractor also. So at a particular layer we can, that representations means how much dimension we want to reduce. Okay, and that reduced dimension we can use for further classification, or based on the problem we can use. Okay, so here you can see training accuracy is 100% in that latent space, and testing accuracy is 95.26%. That's good. Okay, in a same way we have another model like variational autoencoder, where what we have to do here, we are in the basic autoencoder, what we are trying to reduce the image size. Okay, or that vector, latent vector we try to reduce, or trying to get that latent vector. But in variational autoencoder what we have to do is we try to learn the latent space. Okay, means the distribution of that latent representation. Okay, well, not only the vector, we try to learn the that latent space where, and from that space we resample the things, and from the resampled image we try to generate the new image or reconstruct the original image. Okay, so this is the difference between autoencoder and variational autoencoder, where in autoencoder we just reduce the dimension and we get the latent vector there. Okay, and then from the latent vector we try to reconstruct the original image or original thing. Okay, but in variational autoencoder, what we have to do is we try to learn the space or means space, and from that space we resample the thing, and by resampling we try to reconstruct the image. Okay, so from this example we can see variational encoder. So from this notebook, so here comes at that point in autoencoder only we have binary cross entropy loss, but in this case we have two loss. One is reconstruction loss, that is binary cross entropy we can select, and another one is KL divergence loss. That say that okay, how your means this represent the how your sampling or probability distribution of any task is, means how different probability distribution are similar or dissimilar. If they are similar, then your tail divergence value will be very minimum, and if they are dissimilar, then the tail divergence value will be very high. Okay, so both things, both loss we will generate, and by adding both loss we can try to learn the things. Okay, so latent space, so in the first encoder part we try to learn the means the coefficient of that distribution. Like suppose we try to reduce means the mean and the covariance matrix of that space. Suppose we are trying to means normal distribution, we try to learn from there. So from all the images we try to learn that mean and covariance matrix or standard deviation of that space, and by resampling from that space we try to learn the things. And then means suppose we have selected from Z1 and Z2, there means two images we have generated from that space, from the latent space, and we try to measure the KL divergence between these two images. Okay, so that reconstruction loss or plus KL divergence between these two images will be the total loss of the system, of the model. Okay, and then we train based on that. Okay, so next thing is means suppose we try to means only we need the reconstruction loss that will reduce your dimension of the things. Okay, so if we see, if we learn the same thing, if we run the code here, okay, so after importing all the packages and setting the features here, so here you can see total number of means what is the learning rate, what is the number of epochs, batch size, number of features. Original feature is 784, that is 28 plus 28. Then number of hidden 500, intermediate layer, and latent is 15. Okay, and from this space we try to get reconstruct the things. Let's see. First we build the encoder, and here what we are returning, variance, this part we are learning Z mean and variance. Okay, these things we are returning from the encoder part, these things. Okay, and in decoder part we try to reconstruct the thing, and by using this mean and standard deviation we take the sample from there, and from that samples we will try to reconstruct the thing. Okay, and here you can see the loss, means after means encoder part we have returned from this model, and we have computed the KL divergence loss here. KL divergence, so that means we have, suppose we have two probability distributions, and we try to means measure the similarity or dissimilarity between the both space. Okay, so the total cost will be reconstruction loss and KL divergence loss, and then we learn the, so after training we will get the sample. So that will give you, means suppose we have all the numbers are reconstructed in a different space, and from that space it will reconstruct the image, means it works like a generator. Okay, so we can generate anything from the latent space. Okay, So encoder part we will discard, and we only consider the latent space, and from the latent space we take the sample, different samples to reconstruct different, suppose in the digit case, reconstruct different digit. Okay, and how it will deviate, that image will deviate from one number to another number, means how they are similar or dissimilar. If similar numbers are reconstructed, that will be grouped at one place, and if dissimilar numbers are there, then that will be far apart. And suppose we are learning from 1 to 7, so 1 is grouped at one place and 7 will be the nearby, because 7 is almost similar to 1, right? In the same way, 7 is reconstructed into 9. So 9 and means, so that will be the nearby of that things. So in this way, we can reconstruct the thing, and that grouping will happen based on that. Okay. So this is the variational autoencoder. Next model is also conditional variational encoder. So what we have to means apply some condition on that. And suppose from that network we only want to predict something or generate a particular number. Okay. So along with the input, that desired input we also provide to the model. And suppose from that case we want to generate number 3. So 3 is also given to the encoder part, and the decoder part also we have that 3. Okay, and based on that we learn the system or model, and learning will happen. So that variation is called conditional variational autoencoder. The same condition we can also push to simple autoencoder. So conditional autoencoder condition. Okay, so in this way we can switch from one method to another method. We can also control the total loss, like means reconstruction we can make 0, or only we can consider
Excuse me, sir.
the divergence loss. So the impact of that things we can measure. Okay,
Excuse me, sir.
so that we can control in our code. So any doubt? I think
Yes, sir.
we all give the means take the idea from this one autoencoder, how we can use and how we can take the different variations of the things.
Sir, what is the difference between general autoencoder and variational autoencoder?
Hello.
Hello.
Hello. So any doubt?
Sir, I have a question.
Yes, yes, please.
Sir, so what is the difference between variational autoencoder and the general autoencoder that you discussed?
Yes, actually, in general or basic autoencoder, what we have done, we just means in encoder part from the original space means original vector to reduced vector we have just received. Okay, means suppose we have the in this examples we have 768 number of features. Just we try to reduce at 50 or 2. Suppose 2 we have generated. Means from that features to we have reduced the reduced feature is of size 5 or 2, and from 2 to again we reconstruct 768. Okay, but in variational autoencoder we learn a distribution. Okay, and from that distribution that will be the reduced so from the encoder we try to generate some different distribution there, where all the number will be mapped to that distribution, and from that distribution that will be the latent distribution. At that point we are learning latent vector, only one vector we are learning, but here we are learning latent distribution, and from this latent distribution we resample the thing, and from that resampling we generate the different digits. Okay, we can see the image with that wait. I think in this one. Okay, see. This is the component. Is it visible to all of you? So this is the original input 2 and encoder part, and this is the compressed representation of 2. And from this compressed representation, we reconstruct that input. Same input we try to generate. Okay. But in this part, in this one, see, in denoising, in super resolution, and then we are talking about the rational output. Okay. So here you can see traditional autoencoder reduce the dimension of the input data somehow. There is figuring out the important features of the input images. However, latent vectors often don't make such much sense. But on the other hand, to generate train generative models, it is better to have some understanding of the latent space. This idea leads to the variational autoencoder. So here means we are learning in the normal distribution things, what is the mean and what is the covariance matrix. So here we learning this thing, and based on these things we resample the thing, and again we try to reconstruct the things. So you can see here, this is the difference. Suppose 3 we have passed as an input, and encoder will generate the latent space, and from this space we resample and give to the decoder part, and we try to reconstruct or generate 3 from there. Okay, so this is the difference between autoencoder and variational autoencoder. Okay.
So, excuse me, sir.
Yes, please.
Sir, my question is there is a novelty because sir, autoencoder is very old thing. So anything that is the new direction for the research because everybody is asking now.
From variational autoencoder, we can switch to GAN model, because we are generating from this space now. So from here only we have generator and discriminator, right? So after variational autoencoder, we have implemented that GAN models we can learn. Okay.
Sir, GAN is also old. No problem is
That is old. Okay, that is old, but we can have the reduction things. So we can means this latent space, how we can learn. We can means take the inference from there, and this latent space we can use to reconstruct or generate anything.
okay, sir.
Any other question? So we can stop now.
Yes, sir.
Thank you everyone for joining.
Thank you, Dr. Mukesh sir, Anupul sir, for delivering such an insightful and highly engaging hands-on session. Your clear explanation of the concept combined with the practical implementation made the session both informative and interactive. I would also like to thank all the participants for their active involvement throughout the day. Thank you so much, all the participants. Today's session is over, and we will meet again tomorrow for the next session, which will start at 10 a.m.
Thank you everyone.
Thank you.
Okay, thank you everybody. So we are ending this meeting here. You may leave. We will meet again tomorrow. Thank you. There is no more session today.